This video is going to refresh on writing conclusions, which we have to do at the end of every hypothesis test and confidence interval. So we'll start with hypothesis tests. In this question, we have a company that makes hotel toilets. They have a new design which they claim is going to reduce the average amount of water used. And to test this, they take a random sample of 30 of their old toilets and 30 of their new toilets, and they measure the amount of water that it uses. We have some sample statistics here. Mean and standard deviation for their current model, we'll call this the old one, and mean and standard deviation for the new model. Okay, they run a hypothesis test, we get a really low p-value, and we're being asked to write a conclusion. Anytime we're asked to write a conclusion, we're going to write those two sentences from phantoms. We're going to either reject or fail to reject the null hypothesis, link it to the p-value, and then write that sentence about the alternative hypothesis. So that said, it's a good idea to always figure out what our hypotheses are going to be. So we'll start with that, and I'm going to define the parameter as my first step here. So we have the mean amount of water used in both the old and new models. So we have two different parameters here. Mu O is going to represent the true mean amount of water used per flush in the old toilets. Mu N is the same for the new toilets. When we have two sample tests, the null hypothesis is always that there's no difference between the two, and the alternative comes from the problem. So in this case, the new toilets should be better than the old ones. That's the whole point of the company doing this test. And if they're better, they should use less water. So it depends on how we write this. So I wrote mu O first, and if I added that mu N to the other side and put it over here, the old is going to use more water than the new. So I would use a greater than sign. But if these were in a different order, that sign would switch around. It would be a less than sign. Okay, so it depends on how you write it. It could be okay with a less than sign here if those variables were switched. This is a two sample t-test. We know it's a two sample t-test because to start we have two samples. All of our data is quantitative. We have a mean and a standard deviation. If it were categorical, it would give us proportions or data that we would switch into proportions. All right, and quantitative data is always t distributions and not z distributions. When we write our conclusions, okay, first off, we're going to look at our p-value here. It's really, really small. So what that's telling us is that given that the null hypothesis is true, okay, so if there actually is no difference in the average amount of water used per flush, the probability of seeing a difference this large of 1.64 in one group of 30 and 1.09 in another group of 30 is extremely small. It would never happen in real life. So because we saw such an unlikely event, our conclusion would be that this initial assumption is incorrect. Okay? More likely than the fact that we just witnessed an incredibly rare occurrence is that this is actually not true. We're going to reject that initial assumption. The more likely explanation is that the alternative is true. Okay, so our first sentence, reject the null hypothesis because the p-value is very small. We need to say that. The second sentence is always about the alternative hypothesis. We want to write this in context. There is sufficient evidence to suggest, and then we just write this in the context of the problem. Sufficient evidence to suggest that the new toilet reduces the mean amount of water used per flush when compared to the old toilets. Now I wrote what each of these mean over on the side here, just to kind of help explain what this problem is about. On the actual AP exam, you shouldn't do this, leave this off. Okay, we kind of define our parameters up here. We write our hypotheses. Writing these just gives the graders an opportunity to nitpick your answer. You don't need it, and if you don't need it, you shouldn't write it. So this is there just for assistance in explaining this problem. Don't write these explanations when you do a hypothesis test. Next up, in this problem, we have a sample survey where they interview 500 females, 500 males. They're asking them, did you work last summer? And they want to see, is there a difference in the respective populations of these groups in the proportion of students who worked last summer? They do a two-sided hypothesis test, and instead of giving us a p-value here, they give us a z-score. Write a conclusion in context. So again, let's write our hypotheses, starting with defining our parameters. It's a proportion problem this time. We don't have a mean and a standard deviation. In this case, we have data that we can switch into a proportion. So 410 out of 500, for example. So PM is going to represent the true proportion of all male college students who worked last summer. PF is going to represent the true proportion of all female college students. Null hypothesis is that there's no difference between the two. It's telling us that this is a two-sided test, which means our alternative is that it's a not equal to. Okay, again, these are written here, but you should not write them. Two proportion z-test, for reasons I just explained. Proportion problems are always z problems. Now, this one gives us a z-score, but not a p-value. Okay, and with a test statistic, a z-score like this, we can write a conclusion just because this is an unusual z-score. It's more than 2 standard deviations from the mean. And we can use that as our justification. We also could jump to normal CDF. Okay, this is going to be, let me squeeze this in like over here. Highlighter. It would be a left-tailed test from negative 3.14 over to the left. Okay, so I put in like -9 for my lower, upper, the mean and standard deviation, we just keep what it is. And we have to double it because it's two-tailed. I think I just said it was left-tailed. That was incorrect. It's on the left side, but we have to double it because it's a two-tailed test. And we get this for a p-value. So that's a really small p-value. Again, this would be really unlikely to happen by chance. So our conclusion would be to reject the null hypothesis, right? It's the reason that we're seeing such an unlikely event is because our initial assumption is incorrect. That's the conclusion we would make at least. And instead, it's way more likely that the alternative is correct. All right, and the alternative is saying that there is a difference in the proportion of male college students and female college students in those overall populations. And I'm saying population proportion here because it's a good idea to avoid past tense when you write these, but it's hard to do that in this problem because it's talking about working last summer, which is a past tense problem. Now, just to note, when we write a conclusion for a p-value like we just did, that's different than interpreting a p-value. So when we're asked to interpret a p-value, we start by looking at our hypotheses, and our first sentence when we interpret a p-value always starts with, given that the null hypothesis is true. Okay, then we just state whatever the null hypothesis says. So in this case, the null hypothesis is saying that there's no difference in the population proportion of males and females who worked last summer. Okay, so we say if the null hypothesis is true, we say whatever it is that the null hypothesis is saying. Okay, and then we follow it up with defining the p-value. So the p-value is the probability of observing whatever we saw in our sample. So there were differences in those samples. The probability of seeing differences at least as large as the ones that we saw in our two samples is 0.0017. That's what we write when we interpret a p-value, different than writing a conclusion, which is just the reject, fail to reject, sufficient evidence statements. All right, we're back to our toilet company. Same data. This time it's asking us to interpret a 95% confidence interval, and it's giving us the actual interval here, 0.425, 0.675. Okay, it also could word this as write a conclusion. All right, so we have our same parameters as before. Okay, this is a 2-sample t interval, just like the other one was a 2-sample t-test. Now, when we write this interval, you guys tend to write it like this. We are 95% confident that the true mean difference in the water used by the new toilets and old toilets is 0.425 to 0.675 gallons. And that's not wrong, but it would likely miss out on full credit because it's not indicating which of these toilets is more efficient. Okay, so there's probably something in this rubric that's going to require you to note that the new is better than the old one. So the better way to write this answer, okay, ties into the fact that when we put this into our calculator, all right, we're putting it in a specific way, or it's noting it in a problem, okay, saying we're doing the old toilets minus the new toilets, okay. We would put in the 1.64 minus 1.09 if we did all the math for it, All right, so the old toilets are using more water. So when we write this, it's better to write it like this. We are 95% confident that the old toilets use between 4.25 and 0.425 and 0.675 more gallons per flush on average than the new toilets. Key things to write when we interpret an interval or write a conclusion for a confidence interval. You need to have the confidence level. So say we are 95% confident. It needs to say something about mean or average, okay, for quantitative problems, or proportion for categorical problems. And last problem, Tanya wants to estimate the proportion of her school seniors who plan to attend the prom. She interviews a simple random sample of 50 of the 750 seniors in her school and finds that 36 plan to go to the prom. A 95% confidence interval is created as 0.596 to 0.844. Interpret the interval. So define the parameter. Let P represent the true proportion of seniors at Tanya's school who plan to attend the prom. You don't need to do this when you interpret the interval. I just find that it helps when it comes to actually writing that interval. Also, let's name the actual method here, so we would know how to put this into our calculator. So we have one sample, the 36 out of 50 students. Okay, it's categorical, which means it's a proportion problem, and proportion problems are always Z. Okay, and we obviously know it's an interval because it says it explicitly there. So it gives us this. The actual answer is this next part here in green. We are 95% confident that the true proportion of seniors at Tanya's school who plan to attend the prom lies between 59.6% and 84.4%. Okay, note that there's another thing they can ask you, just like in the hypothesis test. It might ask interpret the p-value. It might ask write a conclusion for the p-value. In these problems, it might say write a conclusion or interpret the interval, but it could also ask you to interpret the confidence level. So if it asks this, you would say something like a confidence interval created using this method will capture the true proportion of seniors planning to attend the prom in 95% of all intervals. Okay, a separate wording, which essentially means the same thing. If we collect many samples and create confidence intervals for each sample, approximately 95% of those intervals will contain the true proportion of seniors at Tanya's school. So every time we take a sample, we would get a different interval. There's nothing special about this interval. It'll change with every sample that we take. We're just saying that 95% of the time that we make an interval, somewhere in this range is going to be the true proportion of seniors that actually plan to attend the prom.